The Biography of the Earth, Chapter 10. In this lecture, we'll be discussing the history of the Earth. So let's ask ourselves, is the Earth unique? Well, it's the right planet. It is the correct size to support life as we know it. If the mass of the Earth was different, the atmosphere would be very different. For example, if it was larger, there'd be too much ammonia and methane. If it was smaller, there'd be too little oxygen and water. Also, the molten metallic core, it generates our Earth's magnetic field, and the Earth is being bombarded with cosmic rays that would strip away our atmosphere. Also, plate tectonics. Without plate tectonics, the Earth would be covered entirely by water. So we talked about flux melting and partial melting with the formation of continental crust. And so without plate tectonics, we may not have any crust above sea level. The next is it's the right location. And this basically is related to the distance from the sun. If we were just 10% closer, like Venus, our atmosphere would consist of mainly carbon dioxide, which is a greenhouse gas, so it would be too hot for higher life forms like ourselves. If we were just 10% farther from the sun, it would be too cold, the oceans would freeze, and there would be no liquid water or the water cycle, so no higher life forms like ourselves. Also, the right time. The atmosphere has evolved over time. So we'll talk about how our oxygen has steadily increased with certain organisms and how the atmosphere has changed throughout time. So it hasn't always been hospitable for us. And also, it took a very long time for geologic events to shape the Earth. Okay, so when we talk about our formation of our continental crust, when we talk about these large continental land masses, these took a very long time to form. So we'll talk about that as we go along. Fossils are important clues to Earth's past. So let's talk about Thomas Henry Huxley. He used chalk. Chalk is limestone with microscopic shells, and he used that chalk to demonstrate that the geography and the inhabitants of the Earth's past were much different than today. And these are fossil ammonites, and these are very different from the life we see today, and they give us a lot of context. And that context is showing the evolution of life in the geologic column. There are important terms we will be using. So GA stands for giga años, which stands for billions of years. And MA stands for mega años, which stands for millions of years. So this is a depiction of Earth's history. So we'll start off with our solar system formation about 4.6 billion years ago, and early Earth was molten during the Hadean. Then we see our origin of life and our earliest fossils. This is where we move into the Archean, and this is named after Archaeobacteria. Those are extremophiles. They live in very hot environments like hot springs or very saline environments. So they live in extreme environments. And then we start seeing complex life appearing, and we see our stromatolites. These are photosynthesizers, so we start seeing the oxygen increasing in our atmosphere. Now, down here we have what's called the Paleozoic, and we'll go over these different features. And this is ancient life. So this right here starts our Phanerozoic, which is visible life. And so this is where we see an explosion of life in the rock record. And so we see abundant hard parts like shells, bones, teeth, fish scales, those start appearing. And so remember, our fossilization, it prefers hard parts. So we start seeing an explosion of life in the rock record. Okay, so that's our Paleozoic. Then there's our Mesozoic. You'll probably remember that. That's middle life. That's the age of the dinosaurs. And then down here we have our age of the mammals. That's called the Cenozoic. We're going to start off in the Hadean. And this is named for the Greek god of the underworld, Hades. And during this time, early Earth was molten. So this was 4.54 to 4.0 billion years ago. And during this time, there was a process known as differentiation. This is where the heavier elements sink toward the center of the Earth's core, and the lighter rocky components basically moved outward towards the edge, like the mantle and the crust. And during this time, Earth grew from the accumulation of planetesimals. Now, the Hadean Eon marks the beginning of our Earth's history. And so this was called the Precambrian. And this portion that we're going to be discussing right here, 4.6 billion years ago, represents 88% of Earth's history. So it's not to scale in the geologic column. And when we talk about the age of our Earth is 4.6 billion years old. Nebular theory discusses the formation of the solar system, and it is where there's a large, slowly swirling nebulae. A nebulae is gas and dust clouds between the stars that formed after 200 million years of the Big Bang. And the swirling cloud of gas and dust eventually collapsed, leading to the formation of a protostar. So that's before we had our sun, the pre-star, and then a star, which is our sun. And this is a nebulae, so this is a cloud of gas and dust in space. So when we talk about the formation of our solar system and our Earth, when we apply that to planet formation, we started off as a protoplanetary disk. This is basically an accretionary disk around a young star from which a planetary system may form. And there are planetesimals. These are solid bodies that come together, and basically those can form a planet. And then we have our protoplanets, which are bodies that grow by accumulation of planetesimals, but they're not quite big enough yet to be considered a planet. And this is showing that protostar, and our nebulae was spinning, kind of like this figure skater here. And that protostar was a really dense body of gas that started collapsing inward due to gravitational forces. And eventually a protostar may become a star. Now, this is an image of planetesimals. The Earth grew from an accumulation of these solid bodies. When we talk about the distribution of our planets in our solar system, we have our terrestrial or rocky planets near the center. During the early formation of our solar system, the heat was very intense. It burned off many of the gases in the central rocky planets. And so we have Mercury, Venus, Earth, and Mars. And in the outer portions of our solar system, we have our Jovian planets, or our gas giants. And so these are like our Jupiter, Saturn, Uranus, and Neptune. During the early formation of our solar system, the gases burned off from the interior portion of the planets. So what we had were the terrestrial planets. These are our rocky planets, like Mercury, Venus, Earth, and Mars. Beyond that, we have our Jovian planets, or our gas giants. And these still have a smaller rocky core, but the gases are the predominant part of that. So this is Jupiter, Saturn, Uranus, and Neptune. During the Hadean Eon, there was a process known as differentiation. This is due to internal temperatures of planetesimals increasing as their sizes increased. And melting occurred internally, and it formed a metallic core and rocky mantle. So basically, during the Hadean, early Earth was molten, and during differentiation, iron and nickel The heavier elements that were more dense started sinking towards the center, and the rocky, lighter elements that were less dense started to rise toward the surface. Okay. We also see formation of the moon, and this is due to Earth's collision with a protoplanet that led to the formation of the moon about 4.53 billion years ago. And what happened is the moon formed from these materials that were blasted from the Earth by that collision with that protoplanet. Now, what did the Earth's surface look like? It was likely molten for millions of years before it cooled into a solid crust. And this is just a paleoartist reconstruction of the Hadean. Now, there's some meteors that are coming down. There's lava. Now, early Earth was molten, and the surface of the Earth probably was a lava ocean. What was early Earth's atmosphere like? We know that process known as outgassing. That's those volatile or gassy elements that come out of a volcanic vent. They formed our first primitive atmosphere. And Earth's primitive atmosphere consisted mainly of water vapor and carbon dioxide. Those are the number 1 and 2 gases that are coming out of a volcano. Now, this process still continues today. So during a volcanic eruption, there are pyroclastic material that come out, aerosols, and also gases that are bubbling out of volcanic vents. Let's move into our Archean eon. That was 4.0 to 2.5 billion years ago. There was a period of late heavy bombardment by meteorites. Our oceans formed. Our atmospheric carbon dioxide dissolved into the ocean, and there's still exchange between our atmosphere and our oceans today. Our atmosphere became primarily nitrogen. Plate tectonics began. Continental crust appeared, and early life appeared. There was a period of late heavy bombardment, 4.0 to 3.9 billion years ago, when meteorites bombarded the inner planets. Now, these may have pulverized and remelted the Earth's crust between 4.0 and 3.9 billion years ago. And the reason why they believe it remelted is because there was few rocks that are older than these that remain. There's still some minerals that do remain. And remember, those radiometric datings, those record closure temperatures. During the Archean, we see our first continental crust appear. At convergent plate boundaries, oceanic crust subducts into the mantle. And remember, we talked about flux melting, and we talked about our partial melting, where basically minerals melt over a range of temperatures. The first to melt are those felsic minerals. And so the remaining magma is higher in silica. And so what we get is volcanic island arcs forming on the surface. Okay, so imagine that volcanic island arc, plate tectonics continue. Eventually they collide into each other and form larger land masses, and they get basically sutured onto each other as they collide. Now imagine all these volcanic island arcs, how they suture or are accreted onto each other. As they get accreted onto each other, these small island arcs, how long it would take to form a large continental landmass like we see today, billions of years. We also see our early life. This was 3.2 billion years ago. Our stromatolites first appear. Now these are called prokaryotes. They didn't have a true nucleus. And these are our first known organisms. These are single-cell bacteria, and they lacked a nucleus. And a type of prokaryote is Cyanobacteria. This is one of the groups of prokaryotes. It uses solar energy to synthesize organic compounds, thus producing their own food, a process we know as photosynthesis. And these are recorded in the rock record. There's fossil evidence of these bacteria that include layer mounds of calcium carbonate and or algal mats called stromatolites. So on the right, this is a 3.2 billion year old chert from South America, and it has some fossilized bacteria of archaea. And on the left, we have some stromatolites. These form from cyanobacteria. We have these layered structures of stromatolites that are the remains of the cyanobacteria. And how they form is basically these photosynthesizers harness the energy from the sun and photosynthesize. And basically, the tide comes in, these live in tidal environments, and it covers up those cyanobacteria. So the cyanobacteria start growing up into the sunlight. And how do we know that this is how they form? We have modern day stromatolite mounds in Shark Bay in Australia. And these are in tidal environments that bring in sediment and that basically covers up the cyanobacteria, and they start growing upward into the sunlight because they're photosynthesizers. The next is our Proterozoic eon. This was 2.5 billion years ago to 541 million years ago. And during this time, there was what was called the Great Oxygenation Event that happened roughly 2.4 billion years ago. And just after that, we get large deposits of what we call banded iron formations or BIFs. And during this time, we see formation of really large continents like Rodinia and Pannotia. And we start seeing eukaryotes develop. These have true nucleus. And we also see snowball Earth. There were Proterozoic supercontinents. Supercontinent is all the continents fused into one single landmass. There was Rodinia and Pannotia. So this is a depiction of Rodinia about 750 million years ago. Now this outline here is of modern day South America. Inside of it is Amazonia. And right here we have Laurentia. We know that as our modern day North America. And Rodinia formed about 1 billion years ago and lasted until about 700 million years ago. Now, pay attention to these continents over here. You'll notice they basically move to the other side of Laurentia. And here's Pannotia, about 570 million years ago. And notice again, Laurentia. Basically, all the continents have moved to the other side. This is another supercontinent. And you'll see Amazonia, and you'll see an outline of Africa. And this resulted in the supercontinent of Pannotia, and it began to break up soon after it formed. Now, during this time, we also have the Great Oxygenation Event. This is where we have our oceans saturated with oxygen, and they start precipitating out iron oxides. These are called banded iron formations or BIFs. And this happened 2.4 to 1.8 billion years ago. So remember, prior to this, we see our photosynthesizers. So our atmospheric oxygen levels start to increase, and then we have our banded iron formations or BIFs precipitate out. With the Great Oxygenation Event, we have banded iron formations or BIFs. These are iron oxides that settle out of the ocean. Now, these are from the Upper Peninsula of Michigan, and this is from the chemical precipitation of iron oxides. Now, the gray is hematite, and the red stripes here are jasper, which is the same chemical composition as quartz. So it's high in silica. And these are some microscopic video of some banded iron formations that we have in the classroom. So these red are jasper and the gray is hematite, that iron oxide. And they're quite beautiful. Now, what did life look like in the Proterozoic and climate? We start seeing photosynthetic organisms increasing the oxygen. And we have more complex eukaryotic life that those forms develop. And eukaryotes have a true nucleus. Now, during this time, this is the Ediacaran fauna. This was an artist's reconstruction. Now, as you'll notice that the organisms are very different than what we see today. During this time, we also have snowball Earth. The climate cooled, forming very large ice sheets. And we also have glacial till that's found at the equator. And so glacial till is a very unique deposit that we find at our glacial sediment. And so it's basically a jumble of mixture of different grain sizes that are picked up and churned up by the movement of a glacier. This is some Proterozoic glacial till from an outcrop in Africa. Now, till has varying grain sizes, so very small to very large. And one of the things that's unique about glaciers is they can pick up very large grain sediments. They can pick up sediments the size of a refrigerator or the size of a car. And so this till has varying grain sizes, which is very unique to what we see with glacial deposits. And these strata contain very large clast surrounded by mudstone, like a glacial flour, that basically it's churned down into a very fine grain particle. Now, glaciers can carry a wide variety of clasts of all sizes. Now, during the Proterozoic, some, if not all of the Earth may have been covered by ice. Now, there was still photosynthesis that occurred during this time, so it's either to believe that there were patches of areas in the ocean that were still melted, or that the ice was thin enough that those photosynthesizers were able to photosynthesize through the ice. We will now start the Phanerozoic Eon. And the Phanerozoic Eon marks 541 million years ago to present. And the Phanerozoic Eon means visible life. And this is where we see the first appearance of hard parts like shells. And so fossil shells become abundant. So the Paleozoic marks the first appearance of life forms that have hard parts like shells. We also have an increased oxygen in our atmosphere. So during this start of our Phanerozoic, during the Paleozoic era, we see an explosion of life in the fossil record. And remember, the fossil record is biased toward hard parts. So the more hard parts there are, the more they get preserved in the fossil record, okay? Now, when we talk about our Phanerozoic eon, it is subdivided into 3 eras. The first is the Paleozoic, meaning ancient life. That's 541 million years ago to 252 million years ago. The Mesozoic, which is 252 to 66 million years ago. That's middle life, and you'll know that as the age of the dinosaurs or reptiles. And then our Cenozoic, and that is 66 million years ago to present. So that is recent life. Remember, they have the same root, cen, recent. And this is the age of the mammals. Now, during our early Paleozoic, this was our Cambrian and our Ordovician periods. Okay, so we're talking about 541 to 444 million years ago. During our Cambrian and Ordovician periods, our paleogeography, or the distribution of the continents, was dominated by the formation of Pangaea, and much of the Paleozoic will be dominated by Pangaea. So this is composed of Laurentia, which is North America and Greenland, and Gondwana, which is South America, Africa, Arabia, Antarctica, India, and Australia. And also during this time, we have epicontinental seas. And this is where we have sea level rising and our climates warmed. And so we have large regions of the continental interiors that became flooded by shallow seas. Now, this is an image of Gondwana and Laurentia. And the Paleozoic was dominated by the formation of Pangaea. So these are showing the continents during the Cambrian, This is a view of the South Pole and the distribution of the continents about 510 million years ago. Now, this is some epicontinental seas that are covering North America, and this is where the paleo-equator was. Now, this is during the Middle Ordovician, where epicontinental seas covered much of North America, and an island arc off the east coast collided with the continent. What did life look like in the early Paleozoic? Remember, this is starting off with abundant hard parts like shells, so fossils were abundant. So life in the early Paleozoic was restricted to seas, so we just had marine organisms, and it consisted of several invertebrate groups, including trilobites, cephalopods, sponges, and coral. All right, so this is basically a paleo artist reconstruction of the Cambrian explosion. And so the early Paleozoic marine life may have looked something like this. This is a coral. Here's some brachiopods, a straight cone nautiloid or cephalopod, and a trilobite. Moving up the time scale to our middle Paleozoic era is our Silurian and Devonian periods. So this represents 440 million years ago to 359 million years ago. Now, during this time, the paleogeography, we had the Caledonian orogeny. Now, orogenies are just basically mountain building events. We have the Akkadian orogeny and the antler orogeny. This is a paleogeographic reconstruction of the taconic orogeny. Now, during the Caledonian and the Akkadian orogenies, these are mountain building events. Laurentia, which is North America and Greenland, collided with Baltica and Avalonia. Meanwhile, in the west, we have the Antler Island arc that formed. Now, with our antler orogeny, these are called terrains. They will eventually collide with Laurentia and attach to them or be sutured on. Now, during the Devonian, this area of North America was covered by a shallow seas. Now, in the east, with our Akkadian orogeny, that started shedding sediment westward to form the Catskill Delta. What did the evolution of life look like in the Silurian and Devonian periods? We see new invertebrate species, jawed fish like sharks, vascular or woody plants. Here is a paleo artist's reconstruction of the Silurian and Devonian plants. These vascular plants appeared in the Devonian, allowing the first forest to take root on land. So we start seeing plants move onto land. And during this time, lignin co-evolved. And we also have Tiktaalik. This was a late Devonian fossil of Tiktaalik, and this is believed to be a lobe finfish. It's one of the first vertebrates to walk on land, and if you've ever seen any videos of lobe finfish, you basically can lift them out of the water, and they're basically able to breathe. Now, moving into the late Paleozoic era, we have our Carboniferous and our Permian periods. So that's 359 to 252 million years ago. Now, what does the paleogeography look like? We have the formation of Pangaea. Remember, our Paleozoic has been dominated by that formation, and we have the Alleghanian orogeny. So here is a reconstruction of Pangaea. At the end of the Paleozoic, almost all the land masses had combined into a supercontinent called Pangaea. Now, this is the Alleghanian orogeny, and these are when huge mountain belts formed, and it's believed that the Alleghanian orogeny was as high or higher than the Himalayas are today. And We also had coal swamps that bordered epicontinental seas. And we also see the formation of the ancestral Rockies starting to rise in the western part of the continent. Now, what did the evolution of life look like in the Carboniferous and Permian periods? We have these major Carboniferous coal swamps that became the major coal deposits of today. Remember, we talked about how coal forms. It is basically from plant debris that fell in a swamp and is cooked and compressed and transforms over millions of years into coal. We also see amphibians and reptiles. And at the end of the Permian, we see a major mass extinction. Now, this is Dimetrodon. So by the Permian, reptiles such as Dimetrodon had inhabited the land. This is an image of a coal swamp. Now, on the right, this is the size of giant dragonflies from the Paleozoic, and its wingspan is 1 meter. Now, quick question. How did life on land change during the Paleozoic? Plants and animals moved onto land. Now, we're going to move into our Mesozoic. Remember, that means middle life. So we'll talk about our early and middle Mesozoic era. So we're talking about our Triassic and Jurassic periods. So that's 252 to 145 million years ago. Now, what does the paleogeography look like? We spent most of the Paleozoic forming Pangea. Well, in the Triassic, we start seeing Pangea start to break up. And we also see the Sierran Arc beginning. Here is an image of Pangea breaking apart, and it started breaking apart in the Triassic. By the Jurassic period, a narrow North Atlantic Ocean already existed. Now, by the Jurassic, we have immense sand dunes. Okay, so this is cross-bedding that's preserved in these sandstone layers that blanketed the southwestern United States. And we talked about rain shadow effect in our climate section. So as you move further and further within the continent, the air mass gets drier and drier. And so during the Jurassic, we had a very arid environment. These sand dunes are produced in desert-like regions. They can also be found in beaches, but this extensive is a desert environment. So this would have been much more arid during that time. And so you have these cross-bedded layers that are relics of these sand dunes in Zion National Park. Now, what did the evolution of life look like during the Triassic and Jurassic? Remember, this is our Mesozoic time, so the age of the dinosaurs or the reptiles. So our dinosaurs first appear. We have our first feathered birds and mammals appear. Now, these are just a paleo artist reconstruction of some large dinosaurs that roamed the earth. Here's a Stegosaurus. We also have Archaeopteryx. Remember, this is the predecessor to modern birds. And we talked about fossil molds and how these wing foils are preserved on both the wing and the tail. These are characteristic of birds, but it also has other characteristics of reptiles like tooth beaks, a long vertebrate tail, a winged claw. Now we're going to move into the late Mesozoic era. So we're going to be talking about the Cretaceous period. So that's 145 to 66 million years ago. Now, what did the paleogeography look like at this time? We had a warming climate. So due to that, we had rising sea level. We also have the continuation of our Sierran Arc and the Laramide orogeny. So this is an image of the Atlantic Ocean as it's forming. By the late Cretaceous period, about 70 million years in, the Atlantic had formed and India was moving rapidly towards Asia. Now, this image is of the Sierran Arc to the west and the Western Interior Seaway, which was an epicontinental sea. Now, this is a cross section, and it's basically depicting our Sierran Arc. Basically, we have convergence where we have oceanic crust diving underneath, and we get a Sierran Arc, that continental volcanic arc on the surface. And then just beyond that, we have the severe fold thrust belt. Now, in the Cretaceous, there was a long seaway that flooded the western interior of North America. And there was a large continental volcanic arc called the Sierran Arc that grew on the west. And then just beyond that is the severe fold thrust belt. Here's some tilted strata of the Rocky Mountains near Denver, Colorado. And at the end of the Cretaceous, deformation started to shift eastward in the U.S. during the Laramide orogeny, moving from the severe fold thrust belt over to the Rocky Mountains. And the end result was the Laramide orogeny during the Eocene about 40 million years ago. What did the evolution of life look like in the Cretaceous period? We see modern fish appearing. We see angiosperms, which are flowering plants. Those first appeared in the Cretaceous. And we also have our Cretaceous Paleogene mass extinction. So this is just a paleoartist reconstruction of what the Cretaceous would have looked like. We start seeing the appearance of flowering plants. Those are what our pollinators like. So now we move into the Cenozoic era. That's 66 million years ago to present, so recent life. What did our paleogeography look like during the Cenozoic? We finally get our alpine Himalayan chain forming, the formation of the Andes Mountains, continental to oceanic convergence. We see our San Andreas Fault system. We also have a basin and range province due to extension within the continent or rifting. And then we have our global climate cooling. And we have our last major ice age during the Pleistocene, which lasted from 2.6 million years ago to roughly 10,000 years ago. Now, about 50 million years ago, during our Eocene, this is a paleogeographic reconstruction. India had not yet collided with Asia, and Europe and Asia had not yet collided or coalesced into a single landform. Now, India is traveling northward, and so we do eventually get the alpine Himalayan orogeny, and this formed when Africa, India, all collided with Asia. Now, we had rifting that began forming about 25 million years ago in the western United States. So we had divergence within the continent, so continental rifting. Now, due to that divergence, we started having extension or continental rifting, and this produced a basin and range province across the western United States. And it's most pronounced in areas like Nevada, where you have these really high points. Those are called horst, and then low points, which are called grabens. And that's due to extension within the continent. We also have some areas in yellow. These are basically indicating rotation. So we have some crustal blocks that are rotating as well. So we have kind of a complex action going on. But that basin and range province formed due to rifting that happened within the continent. So it basically created these high points and these low points, like what we see all across Nevada, these mountains and then these low points. This is an image of the maximum advance of the glaciers. Okay. And you can see some of the flow direction of those glaciers. And this occurred during the Pleistocene. That was the last major ice age in North America. And it ended roughly 10 to 11,000 years ago when the climate started to warm. Now, what does the evolution of life look like in the Cenozoic era? Now, we talked about the end of the Cretaceous, how there was that major mass extinction, and we had the extinction of dinosaurs. And oftentimes, when you have a mass extinction event, what follows is a niche is open. And so, some other organism oftentimes takes over that niche. And for that niche, it was the mammals. And we are also see our forest and grasslands reappear, our mammals and our birds diversify. In fact, the Cenozoic is the age of the mammals. We also see ape-like primates about 20 million years ago. We see the human genus about 2.4 million years ago, and then Homo sapiens, which is ourselves, about 500,000 years ago. And then Neanderthals and Denisovans, those went extinct by about 25,000 years ago. Now, during this time, giant mammals are ruling the land. This is an image of some hominids. These are our own human lineage that evolved in the Cenozoic. And these are human-like primates such as Australopithecus, which first appeared about 4 million years ago. Now, quick question. Did Homo sapiens live during the Pleistocene Ice Age? Yes. Now, showing 200 million years ago, after Pangea broke apart, to present, this is the way that the map of the Earth's surface has changed over time because of plate motions, as described by Alfred Wegener. So we start seeing that young ancestral Atlantic Ocean open up, and the continents drifted to their current position that we see today. Now, when we talk about evolution, this is basically the evolution of life. And as we talked about with the principle of fossil succession, when we see the different fossils recorded in Earth's history in the rocks, we can see that there has been change. There are things in the fossil record that do no longer exist today. So we see this evolution or change in life. And when there's a change, it's unidirectional. So it's one direction. Now on the left, we have our largest Mesozoic land animal, which is a dinosaur. And there's an inset map that's showing the elephant to scale. And the elephant is our largest land animal today. Okay. Now, when we talk about evolution, it's a unidirectional change. Okay. So that means that transformations never repeat. So with the evolution of life, that is because basically the species that inhabit the earth today are not the same as those who inhabited the planet in the past. So basically those changes, those transformations are not repetitive. So when we look at the fossil record, there are some things that we observe in the fossil record that are very different from what we see today. Now, one more thing I wanted to reflect on in the Cenozoic is human population. Now, there was an abrupt drop in human population due to the Black Death, which lasted a few decades. But now when we look at human population, it doubles roughly every 44 years, okay? So when we looked at population in 2017, there were 7.3 billion people that lived in the world. Now, when we talk about the Anthropocene, that's the human impact on our systems, the sustainability. We talked about all of that. Remember that the International Commission on Stratigraphy is actually considering adding the Anthropocene, and we'll be voting on it next year in 2021 based on those changes that we talked about in the first lecture. So that's one of the things geologists are trying to tackle is, how much impact have humans had on the Earth system and geologic time. All right, thank you.